In MCQ 3, this is a continuation of chemical bonding. So for this question, we're tasked to find out which of the molecules are considered to be polar out of the three, and the best way to approach this question is to draw out the Vesper structure. So for the first one here, we're going to draw your carbon diselenide. So first, drawing out the dot and cross diagram. Carbon and the adjacent group 16 selenide. Selenide would have required a total of 2 more electrons to become an octet configuration. So by itself, it has 6 valence electrons. So same thing for the adjacent selenide that's on the right side as well. Now through this, you will recognize that carbon has no more lone pairs that's left behind. So configuring this into its Vesper structure, we're looking at a linear configuration of 180 degrees. But most importantly, drawing out the polarization, you can see that electrons are tending towards selenide because it's considered to be more electronegative. There is a dipole moment going towards the right. Same for the one that's going towards the left, but because both of the dipole moments actually cancel out, I will consider that the first carbon diselenide to be a non-polar molecule over here. Now take a look at the second option. This is going to be selenium dichloride. So for selenium dichloride, again drawing out its Vesper structure, chlorine is a group 17 element that only requires 1 more electrons to become stable octet. So I'll be sharing just a pair of electrons. So chlorine is really considered to be an octet configuration. For the case for selenium, after sharing 2 of its 6 valence electrons, it's left with 4 more electrons or 2 lone pairs. So this, with a 2 lone pair and a 2 pon pair configuration, we're looking at a band or a V-shaped structure. And since chlorine is more electronegative as compared to carbon and selenium, polarization of the bond will be going towards the chlorine atoms itself. Chlorine atom is considered to be electronegative. You do have a dipole moment that is going towards the bottom left and bottom right. And since both of these dipole moments do not cancel out, you do have an overall net dipole moment, suggesting that for selenium dichloride, this is considered to be a polar molecule. So for number 3, we are drawing your tetrachloromethane. First, in its dot and cross diagram first, you can see that all of the 4 valence electrons of carbon has been used up fully for covalent bonding with the surrounding 4 chlorine atoms. So with that, we're looking at the adaptation of a tetrahedral configuration. And in this case of a tetrahedral configuration, electrons will still be tending towards chlorine because it's considered to be more electronegative. First, approaching the wedge and the dash structure, you can see that there is actually a dipole moment that does not cancel out. This gives you an overall net dipole moment for the wedge and the dash. Now, approaching the dipole moments that is found on the plane itself, you can see that there is also a dipole moment that has not been cancelled out as well. However, these 2 resulting net dipole moments do eventually cancel out, suggesting again that my tetrachloromethane is considered to be a non-polar molecule. So for the case here, the only option that is polar is going to be D, which is 2-oni.